In the previous video, we learned what differentials were. If you haven't seen that video yet, you need to watch that video first. I'll put a pop-up link in this area right here. Engineers use differentials to calculate something called error propagation. So the thing is, when you measure something, let's say a length, that length is going to have some error in it, depending on what tools you use to do the measuring. If you then use that length to calculate something else, like let's say volume, because your length had error in it, your volume is now going to have some error in it. The amount of error in your calculated volume is called propagated error. And I'm going to show you how to calculate that right now. So if you let x represent the measured value of a variable, and then you let x plus delta x represent the exact value, then delta x is the error in measurement. If the measured value of x is used to compute another value, f of x, then the difference between f at the exact value and f at the measured value is the propagated error, which we will call delta y. In other words, the propagated error, delta y, is equal to f at x plus delta x minus f at x. But here's the trick. Propagated error can be estimated by delta y is approximately equal to f prime of x dx. If you watched the last video, then you'll recognize this expression as the formula for a differential. So look at example 1. The measured radius of a ball bearing is 0.7 inches. The measurement is correct to within 0.01 inches. Estimate the propagated error in the volume V of the ball bearing. So they are talking about volume. So understand that the formula for the volume of a sphere is 4/3 pi r cubed. So of course, volume is a function of radius, all right? It's a function of r, not x. So get comfortable with that. When they give us the radius of the ball bearing, r is equal to 0.7. That's like in the past when they tell us x equals 1, but this time it's r. And similarly, instead of dx, we're going to have dr. But the dr is the error, the 0.01. Notice that the formula that we're going to use involves the derivative. So we're going to need v prime. So using the power rule, if we take this 3 and multiply it in the front, this 3 is going to end up canceling out the 3 in the denominator. So we're going to end up with 4 pi and then r squared as we reduce this by 1. So there's your derivative. So now we will use our little formula, the differential formula, to estimate the propagated error. We are going to use delta v instead of delta y because this is the propagated error of volume. And this will be approximated by the differential. And remember, the formula for that is v prime dr. So delta v should be approximately equal to 4 pi r squared, all right, that's v prime. R is 0.7, and then times dr. Since this is the error, we should put plus or minus 0.01, because it's like give or take. So put that in your calculator, and we have the propagated error in volume is plus or minus 0.06158. So we could say that the volume has a propagated error of about 0.06 cubic inches. Now ask yourself, is that a lot? I don't know, it's hard to tell. So it's going to be easier to get some meaning out of this if we look at something called relative error. That's the ratio of the propagated error to the quantity that's being calculated. In other words, the relative error is going to be the delta y divided by the value of the function. If you write the relative error as a percent, it's called percent error. For example 2, let's estimate the relative error for the propagated error in the volume from example 1. So using this formula, but instead of delta y, we had delta v. And so f of x will just be v in this case. In example 1, we already calculated delta v. That was plus or minus 0.06158. So all we need is to divide by the volume v. So let's calculate that kind of off to the side. So v is equal to 4/3 pi r cubed, right? That's the formula for volume. But remember that in example 1, we were told that the radius was 0.7 inches. So we can go ahead and put our 0.7. So I'm just going to put this in the old calculator. So that's giving me 1.43676. So if you do the division, you're going to come up with plus or minus 0.0429. That's the relative error. That means the percent error is about 4.29%.